Okay, so let's write Maxwell's equations again, now with this displacement current. So we know that, oops, sorry, I'm writing the mathematical expression for the divergence, but that's not something that we care about at this level. Let's write it in terms of words. Divergence of the electric field is equal to the charge density divided by epsilon naught. The integral version of this is Gauss's law. The closed surface integral of the electric field is equal to the charge inside that closed surface divided by a number. The divergence of the magnetic field is 0 because magnetic fields don't diverge away from current. They circle around the current. So Gauss's law for magnetism is not terribly interesting. And then electric fields circle around. Sorry, the equation that involves the circling around of the electric field, there's a non-zero term associated with time dependence of the other field. Of course, when things don't change with time, electric fields don't curl around, they diverge only from the source. The closed loop integral of the electric field needs to be, by analogy with this, associated with some time dependent quantity. It's a little more hidden here because since we're dealing with the integral version, it's the magnetic flux that's changing with time that's associated with this. Magnetic fields curl around. We know that in the static case, but there's also now a term associated with changing electric fields in time. And the integral version of that, Ampere's law, right, the closed loop integral of the magnetic field is equal to the constant times the conduction current, enclosed, plus this displacement term, which involves, unsurprisingly, the time-changing flux, not of the magnetic field, but of the electric field. What's now going to emerge is that in certain situations, these equations will become more symmetric. So let's look at these equations in regions where there are no currents or charged particles. So you have some currents and charged particles over here. So you could have some current density, some charged particles sitting around, but not over here. So what do in this, at that location, what do Maxwell's equations look like? Well, there's no density of current, so we have the divergence of the electric field here would have to be equal to 0. Of course, that's equivalent to saying that the integral over a closed surface is equal to 0 if we are in a region over here where we have some closed surface there. The divergence of the magnetic field is equal to 0. Gauss's law for magnetism doesn't change. The curl of the electric field looks like that, and that's unchanged. the integral version of this is also unchanged, but the curl of the magnetic field, now there's no current density here because the current is only over in this region, so this is 0. So we just have this term, and the integral version of this looks like this, where we only have the time dependent quantity, d phi e dt. And so what you notice is that the divergence and curl equations for the two fields, for the electric field here and here, and for the magnetic field here and here, they look a lot more like each other. And in fact, the differential version of the equations display this symmetry more directly. And it's harder to work with these equations, and what we're going to do next is to think about the solution to these equations. So we'll sort of argue or motivate the curl and divergence equations and eventually show that this leads to a wave equation. And so the solutions, in other words, the electric field and the magnetic field, obey a wave equation. And we'll see the implications of that.